Hi guys. So today we are going to talk about 5G uplink channels. We're going to do it a bit differently. We'll talk about 5G uplink channels and their functionalities with some examples, but we're going to also talk about the 5G logs, the UE logs itself, to understand how the 5G uplink channels configurations actually look like and how the mobile itself finds out where the channels are and what is their configuration. So let's start. Let's understand this one by one. So we have already covered this 5G frame structure before. You might have seen the video already. If you haven't, it would be good to go through that. But today what we'll do is that we will focus on the uplink channels, which is this portion of the frame structure. And we'll do that one by one. So the first one that we'll talk about is the random access channel. Now, what is random access channel? That is the RACH channel that the UE requires to access the 5G cell. So in case the UE needs to access the 5G cell, it needs to initiate a random access preamble, and the random access preamble will be sent over the RACH channel, the random access channel. So over here, if you look at this frame structure, I can say that these are my two slots. So this is my time domain. You can see symbols there, 1 to 14 and 1 to 14. So two slots. And this is my frequency domain. So these you can call my frequency domain, the resource block structure. So if we talk about that, then this over here can be a RACH channel. This is where the UE will send the preamble, or this can be a RACH channel where the UE can send the preamble. Now, what's the difference? In 5G, we have different RACH formats. So we have long formats, also called 0, 1, 2, and 3. And then we have short formats, which are A1, A2, A3, and so on. You can see up to C2. So the long formats, as the name suggests, they are longer in time domain. So for instance, this one is a format, let's say 0, so it will go over and span over 2 slots. While the short formats, again as the name suggests, they are shorter in time domain. So for instance, if this is a short format, let's say C2, it will be within a single slot. Now, what's the difference? Why we need both of them? So let's say we have a network where we have a downlink uplink structure where we have, let's say, 5 downlink slots, then 1 uplink slot, then again 5 downlink slots, again 1 uplink slot. So if we have a 1 uplink slot structure, then we cannot use the long format. So what we will do is that we will use the short formats. Similarly, if we have a structure where we have 2 or more uplink slots, then we can also use the long formats, or we can still use the short format. Now, why we have the long formats and short formats, and what is their advantages and disadvantages? So every preamble, it looks like this. We have a cyclic prefix, we have a T sequence, which is the preamble body, and then we have a guard period, a GP. So if you have a long preamble, you will have a longer preamble body and a longer guard period. That means you will have a support for a much longer or a much larger cell radius. While if you are using a shorter RACH preamble, you will have a shorter body and a shorter guard period. That means that you will have a much smaller cell range. So if you're looking for let's say a low band 5G structure in which you want a much bigger cell radius, then maybe a long format will be a better option for you. If you're looking for just a capacity cell, just a small cell, and you want more downlink oriented data, then you might only use 1 uplink slot, and you're not really worried about the cell range itself because it's a small cell. For instance, you would just want it as a capacity hotspot, so maybe you can use the short preamble format. But the question would be how the UE finds out which preamble format is supported and which preamble format it needs to send to access the cell. Now that comes from the signaling flow. If you remember, during network access call flow structure that we have a video on that, this was the call flow, and during that call flow, the eNode B, it sends an RRC reconfiguration message to the UE, telling the UE about all the configuration of the 5G cell. And after reading that, the UE initiates the RACH preamble, the RACH procedure on the 5G G node B. Now let's see what is the relevant configuration in this message which the UE needs to know to find out which preamble it needs to send. So let's say this is the relevant information. We find the PRACH configuration index here. Now the PRACH configuration index, it tells the UE about the RACH preamble format, and it also tells the UE where to send it in the time domain. So it will tell, for instance, this PRACH configuration index of 17 means that it is preamble format 0, and it can be sent in either subframe 4 or subframe 9. And this is all defined in 3GPP 38211. So if you look at the 3GPP table, there are multiple PRACH configuration indexes defined over there, and you can actually look at each value and find out the corresponding preamble format and the subframe location. Now this is the first thing. Then it finds out here the root sequence index. Now this is the root sequence index which we use in the RACH plan. So when you are doing a RACH plan, you need to assign a root sequence index per cell, and you need to assign different root sequence indexes for different cells, at least for neighbor cells. So we'll also go through that in one of our coming sessions when we talk about 5G planning and design. Now here you can see that the root sequence index is 288, and it also tells you about the length of that root sequence index. So that is 839. For preamble format 0, that is 839. Now the next thing it finds out is this one, the zero correlation zone config. This is 11. This is the cyclic shift. So the UE uses this information, root sequence number 288, length 839, and cyclic shift of 11 to generate preambles. So it can perform cyclic shifts of 11 on these root sequences to find out the next preamble index in the sequence. This 11 actually corresponds to a particular cyclic shift size. So we'll also go through that when we talk about the 5G planning and design later. But for now, just understand that once the UE gets this information, it can use the cyclic shift on this length to create new preambles. So next thing the UE needs to know is what power to send this message. So this is received from this IE information element, preamble received target power, which says, let's say, -100. So it means that the UE sends the preamble with the power such that the G node B receives it with the value of -100 dBm. So this is how the UE finds out its power. The next one is the RA response window. Now what is RA response window? The UE sends the preamble and it needs to wait for a response, right? And this is the message, this is the timer which gives you that value. So this is the arrow which tells you about this timer value. So in this case it is 20 slots. So the UE sends the preamble over the RACH channel, then it waits for 20 slots to get the response from the G node B. If there is no response by this timer and this timer expires, the UE will then send the preamble again. So this is how the UE finds out about which preamble to send, where to send, what is the power for that preamble, and also it finds out how long it needs to wait for the response from the UE from the G node B side. So this is what the RACH looks like from the logs or the UE signaling perspective. I hope this is clear from the RACH part. Let's move on then. Now the next portion is the physical uplink shared channel, or the PUSCH. This one is a pretty straightforward channel. If you look at this diagram, the green portion here is the PUSCH. PUSCH is the one which carries all the uplink data. So for instance, if let's say I'm uploading this YouTube video, so the data that I will send in uplink for the upload will be carried by the PUSCH. That also means that the more resources we have on the PUSCH, higher will be our uplink throughput or uplink data rate, or I can quickly upload the video. So if you're uploading your, let's say, a new profile picture, if you're uploading a new video on Instagram or Facebook or YouTube, you will be actually using the PUSCH. Or even if you're sending an uplink, let's say you're sending a WhatsApp message, that is also being carried on the PUSCH. So PUSCH is something that carries the uplink data, and more resources on PUSCH will result in more uplink throughput or better uplink data rates. So this is a pretty straightforward one. The next one is the PUCCH, which is the physical uplink control channel. That is a very important one in 5G, and let's understand some of its basics. Now in this diagram, this upper resource block and this lower resource block, this is the PUCCH, and this is also a long PUCCH because it is, as the time domain structures indicates, it is much longer in time, so it is also called a long PUCCH. Now why do we need a PUCCH? Let's understand with some examples. Now let's say I need to upload the YouTube video. As I told you before, it will be carried by the PUSCH, but I need to ask the GNodeB, the 5G site, for some allocation, right? I need to tell the 5G site that I have to upload a video, so give me resources. So to request that is scheduling request, and that is sent over the PUCCH. So when I need to upload anything, if I need to upload a video, if I need to send a WhatsApp message, if I need to upload a profile picture or a photo on Facebook, on Instagram, I need to request for resources, and that request is sent over PUCCH. So the UE will send a request on PUCCH. This request is called SR or scheduling request. The GNodeB will receive this request on the PUCCH channel, and then it will respond with the downlink PDCCH channel, which will carry an uplink allocation or an uplink grant. Then the UE will send uplink data on the PUSCH, which will carry the actual picture or actual video that we want to upload. So basically, to request the data, we need to send it on the PUCCH. It's the request, and then after we have sent the request, we get an allocation, and the allocation then is an uplink allocation. This is where we actually put our data. Another aspect that we need for PUCCH is whenever we are doing downlink data. Let's say now I'm watching a video on YouTube. If you're watching my video, let's say that is being carried on the PDSCH, and if I'm getting the data on the PDSCH, I need to tell the GNodeB that whether I am getting it successfully or not. That means I need to acknowledge it, or I need to do a negative acknowledgement telling the GNodeB that I could not get the data. This is called RACH feedback, and that feedback is also sent on PUCCH in most of the cases. Remember that if you're sending something on uplink on the PUSCH, and you also need to send a feedback at the same time, then the UE will multiplex the uplink data with the feedback. So because currently most of the UEs, we cannot send a data on the PUSCH, and on the same slot we cannot send the PUCCH together. So we either send the PUCCH or we send the PUSCH. So if we are sending data on the PUSCH and we also need to send an RACH feedback with it, then what we do is that we multiplex the data on the PUSCH with the feedback. But under normal circumstances, if we're not using the PUSCH and we're just using downlink data and we need to send a RACH feedback, then that is sent over the PUCCH. So that is some of the basic concepts that we use PUCCH for. It can also be used for CSI feedback, but most of the time that is also being sent on the PUSCH. Now, as I told, there are two main formats. We can, as per 3GPP, we have formats 0, 1, 2, 3, and 4. Over here, we can see the length of each format. If the length is 1 to 2 symbols, then that is called a short PUCCH, like format 0 and format 2. They are short PUCCH. If the length is bigger than that, let's say 4 to 14 symbols like this, then we call it a long PUCCH. So here if you see, the PUCCH is 1 to 14 over here. So we can call it a long PUCCH. So let's say what is the difference between them and why do we need them? So let's understand it here. This is an example of a short PUCCH. You can see that we have a PDCCH symbol, then we have downlink PDSCH, then we have a guard period, and then we have a short PUCCH. This is over one symbol, let's say, but it is over the whole frequency band, right? So you can say it's more like a vertical oriented PUCCH. But if we talk about long PUCCH, it's something like that. We have PDCCH, PDSCH, the next slot, PDCCH, PDSCH, then a guard period, then an uplink slot, and that uplink slot carries the long PUCCH, which is more like a horizontal structure. Now, why do we need both of them? So let's say we have some data over here in PDSCH, and if we have a short PUCCH over here, we can send the feedback, see, like this. But if we get data here and we need to send the feedback, then we have to wait a long way up till the long PUCCH, which is the uplink slot. So what it means is that if you're using the short PUCCH, we have a much lower feedback latency. That means much shorter delay. While in case of a long PUCCH, we have to wait for the next uplink slot to actually send the feedback. So in case of shorter delay, in case of services that require shorter latency, shorter delay, more strict delay budget, we can use the short PUCCH. And in case of services which require more stability, a better coverage, we can use the longer PUCCH, because longer PUCCH is expanded over time domain, and it is it requires much lesser number of frequency domain resources, so it will have a better power per subcarrier, and it will have a better spread over the time domain, which will have lesser interference impact as well. So we should have a better stable coverage with longer PUCCH, but we will have a longer feedback latency. So how to look at it from the UE log, for instance, how the UE finds out. So the UE gets this configuration like this. For instance, here we get a starting PRB, which is, let's say, 272, and a second hop PRB, which is 0. So frequency hopping enabled. That means we have the starting PRB, the UE will get here, which is the upper PRB, 272. In the next slot, it gets the PRB number 0. So it knows that the first allocation of PUCCH is here, the second allocation of PUCCH is here, and it also gets the format 1, and it also says the number of symbols 14, and starting symbol 0. So it knows that start from here and go up to 14 symbols. So it will, if it is 0 base, so it means 0 to 13, which will be equal to 14 symbols. So looking at this one, the UE will find out the exact PUCCH structure that is being allocated to this UE for this allocation, or for this scenario. So that is how the UE finds out about its PUCCH structure. I hope this is clear so far. If so far is fine, let's move on to the reference signals. Now this is another aspect that we need to know. We have multiple reference signals in uplink. Some of the major ones are the sounding reference signals, also called SRS, or the demodulation reference signals, also known as DMRS. Now again, let's talk about SRS first. Usually the SRS are somewhere right after the guard. So if we have downlink subframe which switches to uplink, so we have some guard period which is blank, then we have some portion of uplink symbol which usually carries the SRS. So if they carry the SRS, the UE will send the sounding reference signals over here. Now what does the SRS do? SRS is basically used for CSI information. In TDD domains, in time domains, in TDD networks, what happens is the downlink and uplink use the same frequency but different time domain, right? They are separated by the time domain, but they're using the same frequency structure. If they have the same frequency band for both downlink and uplink, that means that the frequency response will be same, right? So if I use SRS in uplink and I use the SRS to estimate the channel, I can use this estimation to apply it on the downlink as well, because both downlink and uplink have the same frequency. The frequency channel response will be similar. So in this case, if we use SRS, what we can do is that we can the GNodeB itself can estimate the CSI information, the channel state information, based on the SRS and apply that information on the downlink channels to get a much better gain in downlink, because GNodeB will have a much higher calculation capacity, as well as the SRS will not really be restricted because of the PMI codebook structure. A UE will have a finite PMI codebook structure, codebook count, but SRS will not be restricted by that. The GNodeB can use the SRS to calculate the most optimal value of the codebook of the pre-coding matrix and apply that in downlink to get the most optimum beam and the most optimum coding matrix, most optimum pre-coding gain. So SRS in that case can be used to enhance the downlink beam forming gains as well. The other one is the DMRS. Now DMRS are the demodulation reference signals. They are usually spread over the whole bandwidth, and they are used for the demodulation based estimation for the PUSCH. So if you have demodulation reference signals, they are part of the PUSCH, and that means that if there is no uplink data, there will be no PUSCH, then there will be no DMRS as well. While the SRS, they are more of a predefined periodicity. So even if there is no uplink data, the SRS will still exist. The UEs will need to send SRS whenever their period expires. So if let's say the UEs are configured with a 20 millisecond periodicity for SRS, then they have to send SRS every 20 milliseconds, irrespective of whether they have uplink data to send or not. While the DMRS will only be present when there is uplink data. Now if you can see here, DMRS takes the full symbol over the whole bandwidth. That means they have a lot of overhead. So if we have more DMRS, that means lesser number of data symbols are there for the PUSCH, and that means that the PUSCH capacity will be reduced. So if we have lesser number of DMRS, we have more PUSCH capacity. That means we have more uplink throughput. That means I can upload the videos much quickly, right? But having said that, if you reduce the DMRS and the UEs are in, let's say, medium or bad radio conditions, or the radio conditions are fluctuating, let's say UE is moving for instance, then there will be high block error rate. The GNodeB might not be able to decode the PUSCH because the DMRS are required to estimate the channels properly to find out the demodulation probability, and if you don't have enough DMRS, the GNodeB might not be able to decode the PUSCH successfully. So it is always a compromise. If you are in very good conditions, you can reduce the DMRS to get the higher PUSCH capacity. If you are in poor radio conditions, you need more DMRS to actually get a much better service. Otherwise you will have very high error rate. So that's all from that, but let's quickly recap. So we have RACH, that is to access the 5G cell. We have PUCCH, that is to request for uplink allocation and to provide hard feedback. We have PUSCH, that is to send the actual uplink data. And we have DMRS, that is there to decode the uplink data. And we have SRS, that is there to estimate the downlink uplink channel state information. So this is a simple summary. This is a simple structure, how the uplink channels are there and what we need, what is the information that we get from each, and what is the functionality of each. So hopefully this will be helpful to you all. If it is, please like, subscribe, and do share with others. Thank you so much. Have a nice day.